So, welcome student to the new class of Introduction to Nonlinear Optics and Applications. So, in the previous class we have started a very important concept, and that is the contraction of the indices of D matrix. Today we will start from that point and like to know what is the implication of D matrix and how we can contract the D matrix indices, and if I do, then by applying other symmetries, how it is possible to even find out different components of the D matrix. So, let us see what we have in today's class. So, today's main topics will be two important concepts. One is the concept of Kleinmans symmetry, which we will going to apply to find out the different relationship in D matrix, and second is Neumanns principle. So, what is Neumanns principle, and using Neumanns principle how it is possible to find out the different component of D matrix, that we will going to learn in this class. So, let us go back to our previous class. So, this is the D matrix as shown here in this slide. So, in principle it should have 27 different components. So, as you can see that the number of components are 27, but there are few components which are colored or which are shaded by some color, and these particular components which are colored in a different in a color with the same shades are in fact the same value. That means D I j k is equal to D j k I. So, here we have written these things, that how D I j k and D I k j are same. That means, if I change the indices of the second two term here, then eventually the D matrix will remain same. So, this is this symmetry. Because of this symmetry, we find that there are several terms in the total D matrix which contain 27 terms, and several terms in this D matrix are same. So, 27 terms are eventually reduces to 18 independent terms. That is very important, because using this permutation symmetry we can have now only 18 different terms. So, let us see that here D 112 and D 121, these are same and it is indicated by same color. In the similar way, D 312 for example and D 321 are the same value, they have the same value. So, that is why they are indicated with the same color. So, if I now able to write this D matrix in contraction indices under the contraction of indices, then since I j here j k is equal to k j. So, we will not going to write every time the 3 independent terms like I j k, rather we will contract the indices, and there is a new way to write these components, so that we can now have a reduced form of D matrix. So, I y 1 1 became 1, 2 2 became 2, 3 3 became 3 and so on, 2 3 and 3 2 which is eventually same became 4, and then 3 1 1 3 which are again the same quantity become 5 and so on. So, here we wrote in the some example that D 1 1 should be written D 1 1, D 2 2 written D 1 2, D 1 3 written D 1 3, D 1 2 3 or which is equal to D 3 1 3 2 can be represented at D 1 4 and so on. So, this is very important, because we can reduce readily, we can reduce by applying the symmetry property of the D matrix, we can reduce the D matrix from 27 different components to 18 components. So, last class we discussed this. So, again we are discussing, yes. So, this is the compact form of the D matrix. So, now you can see here we had 27 component and now we have reduced to 8 component. So, now D 11, D 12, D 13 these are changing. So, for every value, for one, say one, if I want to find out p x, then in the right hand side we have 6 terms that we have shown in the previous class. So, 1, 2, 3 is nothing but x, y, z. To understand this thing in a clear way, we just use 1, 2, 3. So, that it is easier for us to understand, but eventually this 1, 2, 3 is nothing but x, y, z components. Well, after having the reduction of this D matrix, the next thing is to apply the Kleinmans symmetry. So, Kleinmans symmetry is nothing but the condition where we assume that the susceptibility is not a function of frequency. Normally what happened, that when we find out the susceptibility term, this susceptibility term was a function of frequency. So, here if I look this transformation, then we can find one interesting thing, that when I find susceptibility term I j k, for example this one, where ith components contain omega 3 term, which is combined by the j kth term. If you remember that p of I, it was epsilon 0 susceptibility I j k and E j E k. That was our main equation in terms of nonlinear polarization. Obviously, P I is nonlinear. So, that is why two component E j and E k is associated with this term. But now, if we have E j component has some value, say omega 1, and E k components had some value, say omega 2, E j multiplied by E k basically give rise to one frequency, which is omega 3. So, my susceptibility is written as omega 3 is equal to omega 1 plus omega 2. So, omega 3 components are generated by omega 1 plus omega 2. Now, if I change the entire permutation, so for example, now I try to find out what is jth. So, jth component contain omega 1 frequency. So, in susceptibility terms, if I look this, so here we can see that ith component are related to omega 3, jth component is related to omega 1 and kth component is related to omega 2. So, now if I make a permutation of these terms, then what happened, this frequency distribution will also going to change. So, omega j, which is related to omega 1, can be represented as omega 2 minus of omega 2 plus omega 3. We know that omega 3 can be represented as omega 1 plus omega 2. So, if I want to write omega 1, it should be omega 2 minus omega 3. It should be represented as minus of omega 2 plus omega 3, which is this term. In the similar way, if I want to write omega 2 in terms of omega 1 and omega 3, it should be simply omega 3 minus of omega 1, which is this. And now, omega 2 is a component related to j, we know omega 3 is related to I and omega 1 is related to j. So, all the combinations, they are same if I consider the susceptibility does not depend on frequency. So, that means there is no dispersion into the system. If we assume this, then all these ijk's components, ijk, jik, kij, all the permutation of ijk components will be eventually the same value, because I am not considering their frequency dependency. So, all the cases I just write omega 3, omega 3, omega 3, which is equal to omega 1 plus omega 2 and so on. So, they are not depend on the frequency at all. So, when I reduce these things, that means omega I j k is, I change this as omega j k I. So, we have additional permutation symmetries. So, this additional permutation symmetries is nothing but the Kleinmans symmetry. So, this Kleinmans symmetry basically tells us I can make a permutation of entire term according to my choice if we consider that the susceptibility does not depends on any kind of frequency. That means the system is eventually dispersionless. Well, if I now look these d terms which was given here having 18 independent terms, now we can have additional terms which are same by applying the Kleinmans symmetry. So, let us try to find out which are the terms which are same. For example, this is the contraction notation, that what is my contraction in terms of 1 1 2 2 3 3, which is going to be 1 2 3 eventually, and this is the 18 different terms in D matrix, D11, D12, D13, D14, D15, D16, all are distinct, D21, D22, D23, D24, D25, D31, 32. So, all are distinct terms here, 18 distinct terms are there. This was our initial D matrix after applying the permutation symmetry. Now, we are going to apply another symmetry as I mentioned, which is Kleinmans symmetry, which suggests that if I now write D211, these components, what should I write? Each one is nothing but 1 1. So, I should write D211. If I write D211, then my Kleinmans symmetry suggests if I make a permutation of this term, so D211 is nothing but D121. If I exchange this 1 and 2, which we can do because it is under Kleinmans symmetry, then it becomes D121 and D121 is nothing but D211 according to Kleinmans symmetry. But if I look D121, it is a different coefficient in terms of this index contraction. So, D121 should be eventually D16. So, 21 we know that 21 is 6. So, I should write it is D16. So, one very important thing that I figure out, that D21 coefficient and D16 coefficient, they are same. In the similar way, we can find many other terms which are same. For example, D25, D26 which are equal to D14, D12 and so on. So, how many terms we find they are same to each other? So, if I calculate, it is 1, 2, 3, 4, 5, 6, 7, 8. So, 8 different terms are there which are equal to same value of other terms. So, that means whatever the independent coefficients here, D matrix coefficients here are not really independent, but there are some kind of symmetry which we call Kleinmans symmetry, under which few of the terms are same. So, if I now write D21, so D16 and D21 they are same, D25 and D14 they are same. So, this 18 coefficient now reduces to, if I use this symmetry 18 minus 8 which is 10. So, eventually we come to a point where we find that D matrix, which looks very heavy initially, and after contraction of the indices we find there are only 10 components are there which are independent to each other. So, if I go to the next slide, we can see here what we are telling, that D11, D12, D13, D14, D15, D16, D22, D23, D24 and D33, these are the coefficients which are independent to each other. All other coefficients can be represented in terms of this. So, if I do, then we find a new form of D matrix, and here we can see that D 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, these are the independence coefficient, but D 2 1 can be represented in terms of D 1 6. Then D 2 2 independent, D 2 3 independent, D 2 4 independent as shown here by shaded terms. All these shaded terms are independent terms, and how many shaded terms are there? 1 2 3 4 5 6 7 8 9 10. So, 10 independent components are here. Other components, if I replace, it will look like this. So, D 1 6 and D 1 6, they are same. In the similar way, D 2 5 I can write as D 1 4, D 2 6 I can write D 1 2, all these things are written here, that which terms is changing to what. So, the important thing here is that we can reduce the number of terms significantly if we apply some kind of symmetry in D matrix. So, after having the knowledge of D matrix, next it is time to find out that what should be the value of this D matrix. Now, how to find out the values, independent values of this or the coefficient of D matrix. In order to understand that, we need to know about Neumanns principle. So, before going to Neumanns principle, let me give you make you a reminder that in the birefringence process where we try to generate the second harmonic, these birefringence things are happening inside crystals. So, crystals are there where we can have the birefringence for which we are getting the phase matching, and this crystal should have some sort of symmetry. So, that means if I apply some kind of symmetry operation, so the crystal will remain same. So, applying this condition, we can have Neumanns principle. So, now let us try to find out what Neumanns principle suggests. But before that, we should understand that since we are using crystals, there are different kind of symmetry in the crystals, we call the point group symmetries. So, these point groups, so some kind of symmetry operation we can make over on the crystal, and if I do that, then what happen that the crystal, the orientation of the crystal will change, but not the property. So, using that thing we can say in the Neumanns principle that the susceptibility tensor of a material belonging to a certain crystal class must be invariant under corresponding point group. That means, if I put some kind of operation over that, then there will be no change on the crystal. So, if we make a transformation symmetry operation over this material, then the susceptibility before and the susceptibility after the transmission must be same. So, if I change if I put some kind of operation, and because of that if the susceptibility tensor changes, then the new susceptibility tensor and the old susceptibility tensor which was before the operation supposed to be the same thing if my operation is a symmetry operation. Well, before going to apply this kind of transformation over a tensor or matrix, let us find out how the vector is transformed over some kind of operation. So, here a very simple example is given where you can identify that this is a rotation matrix. This is a rotation matrix around axis z if the theta amount of rotation is there. So, we have an axis like this, and if I make a rotation, so my new axis is dotted 1 and it is something like this. So, then what happened if I have a vector in my previous say this is x y z, if I write. So, if I have a vector here psi which has a component psi 1, psi 2, psi 3, after rotation of the axis what happened, we have a new component psi 1 prime, psi 2 prime and psi 3 prime. How psi 1 prime, psi 2 prime and psi 3 prime is related to the previous components, the original components psi 1, psi 2, psi 3 can be represented by this operation, which is quite straightforward, and I believe most of the students are aware of these kind of things. So, now the question is what happened when we are going to apply this on a tensor, this kind of operation on a tensor. But before that we generalize the transformation of vector. So, if R1, R2, R3 is a generalized operation matrix, so I can write this in index notation like this. So, ith component is represented by, if I write this I 1 prime, it is represented by R 1 1, R 1 2 and R 1 3. So, it is eventually R I j j. So, now if my transformation, whatever the transformation I am talking about in terms of R is orthogonal in nature, then we have a relationship between the for orthogonal matrix, that is R transpose is equal to identity matrix, that we know. Oh, that means R transpose is nothing but R inverse. So, if my operation is orthogonal in nature, then what happened, we have a relationship between R and R transpose, and R transpose is nothing but the inverse of the R, where R is the operation matrix. So, if every operation can be represented in matrix. So, that we are doing. So, we have an expression like this for orthogonal transformation. Why the orthogonal transformation is important here? Because whatever the operation we are talking about are essentially the orthogonal transformation, and under orthogonal transformation what happened, that we should have a change of vectors, the coefficient of the vector change. But since the orthogonal transformation is there, so there is a additional relationship between the different coefficient of the operation matrix R I j in general. Okay. So, once we have the information of this R matrix, next we try to apply these things over a tensor. So, before doing that, let us try to apply this in our old equation, polarization and electric field equation, and that is this. It will be easier for you to understand. So, this is the P vector which is related to E vector, like P is equal to epsilon 0 chi 1 E, which is straightforward. Now, if I write it in component form, it should be P I is equal to epsilon 0 susceptibility I j and E j. Now, what we try to do? We try to write this P vector in different coordinate system, where this coordinate system is represented by, or some operation is there for which the coordinate system is changed, and this operation is represented by the matrix R. So, that means if I operate R over P, then I will have P prime. So, in component notation, P I prime is R I j P j, which is before, as before we have shown in terms of psi we have the same expression, but here in place of psi we consider that P is there. So, that means polarization term is there. Next, what? The electric field E is also going to change, and electric field is a vector. So, the component of the vector will change in a similar notation. So, E can be represented in terms of R inverse, like R inverse E prime, because if I make inverse both the side, then this will be the case. Then E L component can be represented in terms of E k component like this. So, just I use the similar principle here, I just reproduce the P ith prime component in terms of P j. Here I am doing non prime component to prime component, there is a relation, and I will eventually have this. Why? You can see that R inverse of I j was R of j I, because they are orthogonal. So, these are the relationship they should hold. Well, after having this, now go back to our old equation, that ith component is now going to change. Now, I put all these things together. So, P j is nothing but susceptibility J L and E L, which is this equation. So, I am writing this equation once again. I operate these things over P j. So, P j in terms of E is this. Now, E L again I can write in terms of E prime. So, this is my prime form, which is already I have derived in this place here, that how E L is represented in terms of E k prime. So, in prime frame I just write it. So, P prime which is in the left side and E prime which is the right side, if I now write it all together. So, I have a term here which suggests that this is nothing but this is, you can see the left hand side P is in P prime frame or the prime frame, E k is prime frame. So, this has to be in prime frame. So, if I write this into the prime frame, the susceptibility which is essentially a tensor can be transformed like this. So, this is the rule of transformation of the susceptibility tensor. So, susceptibility tensor I j component in prime frame can be represented in terms of susceptibility tensor in non prime frame J L, and it is related to I j and K L with this notation. Well, after having this general notation, what we can do, that we can use this thing here. So, after the rotation or whatever the operation, it is not necessarily the rotation operation is there may be several kind of operation, we have a general expression here. So, the general expression suggests that we have some kind of, so I have a susceptibility tensor here. In prime frame, the susceptibility tensor I can write susceptibility prime, and if some operation was there, so this is the operation that is operated over psi and I am getting this. So, this is the rule that I am applying some kind of operation on vector, I am getting different vector component. In the similar way, if I apply the same operation over a tensor, then the tensor will going to change in the prime frame, and when the tensor is going to change in the prime frame, this is the rule that we have. This is the rule that we have, that I j k component in prime frame can be represented as R I alpha, R j beta, R k alpha, alpha beta gamma. So, this is the rule of change of a tensor under some kind of symmetry operation, where R is the operation matrix. So, if I j k of susceptibility tensor I j k is changed in this way, so this tensor in the similar way can be changed in this fashion. So, R 1, R 2, R 3, these are the vector components, these are the matrix operation, these are the coefficients, and when we have these coefficients, we can have also the coefficients of d 1, 2, 3 and all these things. So, now if I want to find out d prime under some kind of rotation, then I will going to use these things and operate over that, then individual component can be find out in this way. Okay. So, let us see what we have. So, let us try to understand once again what is Neumann principle. Maybe today's class we will not going to complete that, in the next class again we will start, but the important thing we should note once again, see this important. So, we are going to apply some kind of symmetry operation. So, this is suppose a system we have, a coordinate system we have. So, some kind of symmetry operation we are making, so that my operation system is changing. So, D matrix will remain invariant under this operation, that is the principle, this is the Neumann's principle. So, that means d I j k prime after making this symmetry operation over d alpha beta gamma, then what happened after the operation, whatever the value we have, that should have the same value that of the previous one. So, I j k and I j k, it should be same value after doing this operation. So, this is essentially the Neumann's principle. Once again let me state that in Neumann principle, if I apply some kind of symmetry operation over D matrix components will be changed, and this changing D matrix component will be exactly the same D matrix component before the operation, and from that we can have a relationship between different D matrix component, and we find in the next class that we will start using some example that how the D matrix component will be calculated, and most of the cases we find that D matrix component will going to be vanished or they are same to each other, and then the number of independent coefficient again reduce significantly, and eventually we have 2 to 3 or to 4 different components of D matrix that can form independent terms, and through which we can form the D matrix. So, well, let me conclude here. So, today we will learn a very important concept of this Kleinmans symmetry and Neumanns principle. So, both are applied over the D matrix, and because of that what we find that the number of independent coefficient reduced significantly. Initially we started with 27 different component of D matrix, which is very tedious to handle. Then we find that after applying this kind of symmetries, we can reduce this D matrix up to 10 independent components, and further we will going to see applying the Neumanns principle we can reduce it more, and eventually we have only 2 to 3 different D matrix components which are independent to each other, and we will deal with these things in the previous classes. So, with that note, let me conclude here. Thank you for your attention and see you in the next class.